Afternoon, students. So welcome to rapid revision series. So today we are going to discuss one shot number 10, that is, and the topic is magnetic effect of the current and magnetism. So yesterday we discussed the current electricity. So today we'll be covering the topics from the moving charges and magnetism. What are different topics that we are going to cover today is that. So this one, first one is Biot-Savart law and Ampere-Riedel law. That is the core topic from this magnetism. Second is force on the moving charge in magnetic field, and next is Lorentz force. Lorentz force is applied when both electric field and magnetic field is there. Force and torque on the current carrying wire, and bar magnet and its properties. So these are the topics that we are going to cover in today's session. So for today's session, so some of the key elements related to direction is important, that we use right hand thumb rule, we use right hand palm rule. That direction is also I'll be telling in the class. So let's check what is the weightage wise for this particular chapter we have. That is NEET questions from the 2014 to 2024. So this orange color represents this moving charges and magnetism, and this blue color represents this magnetism matter, where we discuss the bar magnets and properties. So here we can check. So on an average, we can expect together from these two chapters, we can expect 3 to 4 questions on an average in NEET that we are going to cover today, this particular chapter. So let us start. So let's begin. The first one is, the very first topic is the Biot-Savart law. So what do you know Biot-Savart law? Biot-Savart law gives the magnitude of the magnitude of the magnetic field due to current element. So for example, so basic term, that is, for example, if this is the current carrying wire over here, and this particular point you want to calculate what is the magnetic field. So for that, what we have, so this distance is r and this angle is theta. So magnetic field at this particular point is given by dB is equal to mu naught by 4 pi I dl cross r divided by r cube. So this is the basic fundamental, that is Biot-Savart law, that is the dB equals to mu naught by 4 pi I dl cross r divided by r cube, where r is the distance of that particular point from the current element at which we are taking this, for which we are calculating the magnetic field. So it has certain applications. So this particular formula, this is magnetic field due to a small element, not for the complete element, this only for the small element. So there are certain application. First one, that is magnetic field due to straight wire. So magnetic field will be calculating due to straight conducting, so straight wire. So in this case, I'll be writing straight wire. The magnetic field is given by, so let's say this wire is there, and this particular point you want to calculate magnetic field. So just join this point, join this point, join this point with this. So distance r, this angle is, let's say, theta 1, and this angle is theta 2. And current is, let's say, flowing from the bottom to the top. So magnetic field at this particular point is given by BP is equals to mu naught I divided by 4 pi A or 4 pi R into sine theta 1 plus sine theta 2. Sine theta 1 plus sine theta 2. This is magnetic field at point P because of this current carrying wire. Magnetic field at point P because of current carrying wire. So this particular term, now this is the basic term over here. And if we talk about the infinite wire is there, if the wire is very infinite, it is going to infinite this side, is going to infinite this side. In that particular case, distance will be taken here r. So in that case, theta 1 will be 90 degree, and this theta 2 also be 90 degree. So for that, we'll be writing theta 1 90 and theta 2 is also 90. Sin theta 1 90, sin 90, 1 plus 1, that is 2. So what is magnetic field at that particular point in case of the semi-infinite wire? That is mu naught I divided by 2 pi r. This is because of infinite wire, that is extending wire on the both the sides, upward side as well as downward side. This infinite wire. If we talk about the semi-infinite wire, if we have the semi-infinite wire will be, for example, let's say this is the wire over here. At this particular point, we are calculating the magnetic field. It is going to semi-infinite this side. So in this case, theta 1 value will be 0, but theta 2 value will be 90 degree. Theta 2 value will be 90 degree. So what is magnetic field in that case? What's semi-infinite wire? Mu naught I divided by 4 pi r. Putting theta 1 0 and theta 2 90 degree. This is the magnetic field we are getting because of the straight portion of the wire. Next we have, if we have circular loop like this, one loop is there, and let's say number of loops is n. Okay, so one loop is there, n loops, and radius of the loop is r. So in this case, and the loop is carrying current how much? I. So in this case, magnetic field at the center is given by B is equals to mu naught n I divided by 2 into r, where r will be radius and this will be magnetic field. R will radius and this B will be magnetic mu naught Ni divided by 2R. So this mu naught Ni divided by 2R, And suppose where n is the number of turns, I is the current which is flowing through this, that is exactly the center. And suppose if I loop like this, and we want to calculate magnetic field at this particular point, distance of that particular point from here is x, and this one is r. Current is again the same thing in this particular case. So because of this current carrying wire, we want to calculate what is magnetic field. Because this current carrying loop, the magnetic field will be along this side. So magnetic field value will be given by B is equals to mu naught n I r square divided by 2 times of this r square plus x square to the power 3 by 2. What is x here? X is distance of that particular point from the center of the ring. So if the ring is like this and current is in this particular manner, so this point we have to calculate the magnetic field. And what is the direction of magnetic field that we'll be calculating? The direction of magnetic field will be, this is the direction of the current, magnetic field is going inside. Okay, remember this direction of the current, magnetic field is going inside. This is the direction of the current, so magnetic field will be going inside. Inside we represent in terms of the cross, and if it is coming outside, so this is the direction of current. So rotate your fingers in the direction of the magnetic field, and this thumb should represent the direction of the current. So this is the direction of current. We have to rotate our fingers in the direction of magnetic field. So this particular point will be magnetic field which is coming outward. If the wire is like this, and we want to calculate magnetic field at this particular point, so current is flowing this way. So this will be the direction of the current, and downward side we have to calculate the magnetic field. So how the downward side magnetic current wire is so this is the direction of the current, and my fingers is going inside. So direction of magnetic field inside this will be inside, and this side will be outward side. Outward means dot symbol, and this one is cross symbol. If you talk about the circular coil, rotate your fingers in the direction of the current, then thumb will give direction of magnetic field. Rotate your fingers in the direction of the current, thumb will give direction of magnetic field. So in this particular case, direction of magnetic field will be towards outside. If it is this one, if it is this way, that is direction of current is outside. So this particular case, current is in this particular case, current is anti-clockwise in this particular manner, and direction of magnetic field because of this is outward, and this is what we define. This will be north pole, and suppose if it is happens this particular way, so in this case what we define, this way, this will be current is flowing like this, magnetic field will be going into this plane, so this will be, and whatever this particular direction, this will be southwise. This will be south pole, and this will be north pole in terms of the polarity of the loop. This will be north and that will be south. Okay, right. Next we have, this is magnetic field at a certain distance from this, mu naught ni divided by r square into 2 r square plus x square to the power 3 by 2. Suppose if they're asking, this is the, suppose if they're asking the magnetic field because of the solenoid we have. If you have solenoid like this, so remember this, exactly at the end of the solenoid, whatever the current is flowing, so because of the end of the solenoid, magnetic field at the end of the solenoid we have mu naught n I divided by 2. Any point inside the solenoid, the magnetic field is going to be B is equals to mu naught into Ni. Again, on the other end also, this will be B is equals to mu naught Ni divided by 2. So inside any point on this, magnetic field will be given by mu naught Ni. This is mu naught Ni by 2, and this is also mu naught Ni by 2. On the two ends, mu naught Ni by 2. What is N here? Number of turns per unit length. What is I here? I will be current, and you know what is mu naught? 4 pi into 10 to the power minus 7, we call it as permeability of free space. We have permittivity of free space 1 by, that is 8.8 10 to the power minus 7. Here we have permeability of free space 10 to the power minus 7, 4 pi into 10 to the power minus 7, that is permeability of free space. So these are the things that we have in Biot-Savart law, and we also have that not complete circle is given. Suppose if portion of the circle is given and that carries current, and that is making some angle at the center, so because of this portion of the current carrying wire, magnetic field at the center, if you want to calculate, again the direction will have to rotate your fingers in the direction of the current. The magnetic field is going inside, so this side magnetic field is going inside. And what is B value? The B value is given by mu naught I into 2r. This is for complete circle, multiply by alpha divided by 360 degree. If alpha in degree, we will be writing this. If alpha in radian, so this particular term is radian. So B is equals to mu naught I divided by 2r into alpha divided by 2 pi radian. We'll be using this particular when the alpha is given in terms of the radian, and when the alpha is given in terms of degree, we'll be using this particular formula. So if it is semicircle, what is alpha value? Semicircle alpha value is 180 degree. So when the semicircle alpha value is 180 degree, put the value is 180 degree. So what is magnetic field at the center? We'll be writing this mu naught I divided by 2r into alpha. What is alpha? 180 by 360. value we are getting here, B is equals to mu naught I divided by 4R. If it is quadrant of a circle, so alpha value is 90 degree in that particular case. Putting the alpha value 90 degrees, so B is equals to mu naught I divided by 2R into 90 divided by 361, 4. So this magnetic field we are getting here, mu naught I divided by 8R. This is the magnetic field that we are getting in this particular case. Mu naught I divided by 8R, mu naught I by 4R semicircle. For complete circle, mu naught I by 2R. Remember this. Next we have, our next topic is that Ampere-Circuit law. Ampere-Circuit law also used to find the magnetic field because of the current element. The first property that we have, suppose if this one loop, there is one current wire over here. There are, let's say current wire is there and current is flowing in this particular manner. Okay, so two wires are there and one more wire is there that is outside. So we are assuming some hypothetical loop around this current carrying wires and this particular loop, this particular circular loop, and let's say direction on this loop is given by this direction of the loop. So if I see from the topmost side, it is moving like this. Okay, then I will rotate my fingers in the direction of that loop. So I will rotate my fingers in the direction of that loop. I am rotating, the thumb is going outside. So this particular direction will be taken as positive and this particular direction will be taken as negative. So what is this? Integration of B dot dl is equals to integration of B dot dl, that is line integral of magnetic field over this complete length of the loop is equals to mu naught times I enclosed by it. Mu naught times I enclosed by. So this integration of this B dot dl is equals to, we'll be writing this mu naught times I enclosed. What is I enclosed? The one current which is inside the loop, There are three currents over here. The current which is inside the loop, I1, I2 is inside the loop. So this will be mu naught times I1. I have to take it as positive because I am rotating my fingers in the rotation of the direction they mentioned in the given scenario. So this thumb should be positive value and this thumb should be negative value. So this thumb is positive value, so this current should be positive and this should be negative. So this I1 minus I2 and what is that? No I3. Why no I3? Because that I3 is not there inside this loop. So this is what we are getting magnetic field due to integration of B dot dl. Now this particular expression is also we define Ampere-Circuit law, that is integration of B dot dl equals to mu naught times I. So this integration B dot dl is mu naught times I. What is I here? I enclosed. So this entire term depends on inside current only. Depends on I inside only. Theoretical point of view. Questions from theoretical point of view. This entire term depends on I inside only, but this particular term depends on I inside as well as outside. Okay, I inside as well as outside, right? So this thing that we should keep in mind. So and there are certain applications. The first application is magnetic field due to straight wire. Because of this we anyway calculated what is magnetic field distance R. So magnetic field because of this is given by mu naught I divided by 2 pi R. We have because of the cylinder. Now cylinder will be having two types. First one is hollow. So let's discuss for the hollow cylinder only. So suppose if the current is flowing through the hollow cylinder. So if this one is hollow cylinder and current is flowing through it, so magnetic field inside will be 0 because there is no current inside. The current is only flowing on the surface. In that particular case, if taking any particular this particular point, distance of that particular point from the axis that will be taken. So this distance is R. This will be capital R, and this side, this particular point, small r. So in this case, magnetic field, that is mu naught I divided by, that is magnetic field inside will be 0. So B1 value inside any point, magnetic field value will be 0. On the surface, the magnetic field value is given by B2 is equals to mu naught I divided by 2 pi capital R. And outside the surface, again at this particular point, the magnetic field value is given by mu naught I divided by 2 pi small r. And what is small r? Distance of that point from this axis, and that point is distance, how much distance? R, that is outside point. Mu naught I divided by 2 pi r. This is 2 pi capital R, this is 2 pi small r. This is because of the hollow cylinder. And if we have the solid cylinder, solid cylindrical current, so magnetic field due to solid cylinder, current over here. So in the solid cylinder, what we have to keep in mind, current is not same everywhere. Current is distributed. So current is distributed like this over the complete cross section area. So in that case, we have to assume. So if I am taking any one particular point over here, so this particular point I have to take entire current what is coming out this. So this point inside B1 value is mu naught I divided by 2 pi r square into, okay, so this particular term, that is mu naught I into r divided by 2 pi r square. On the surface again the magnetic field value will be the same, that is mu naught I divided by 2 pi r, and outside the surface distance is r. In that case we'll be writing this B3 value. What is B3 value? Mu naught I divided by 2 pi small r. So these are the things that we should keep in mind. So magnetic field inside at any point is directly proportional to r. Magnetic field is inversely proportional to radius, and this value will be constant over on this surface of this cylinder, and this outside point, that is B, is inversely proportional to 1 by r. So we talk about the graph. This particular graph is for hollow cylinder, B versus r, and if we talk about the graph for this solid cylinder, so this graph will be for solid cylinder. So this B versus small r we have. Clear? So this particular point that we have, this is r equals to capital R, this is r is less than capital R, and this side B is inversely proportional to r. This outside point, this will be inside point. This is the magnetic field because of this. This one is for hollow and this one is for solid, right? This one is for solid. So let's see some of the questions from this, that is Ampere's second law and Biot-Savart law. So first one is from Ampere's second law for a long straight wire of circular cross section. Long straight wire of circular cross section. So let's say here we have wire of circular cross section like this, and it is carrying some current. Circular carrying a steady current. The variation of magnetic field in the inside and outside the region of the wire. So they have mentioned circular cross section, straight wire is there, and carrying a steady current. So current will be here. So let's, as they mentioned over here, this will be, they have not mentioned. So let's focus on whether it is solid cylinder, hollow cylinder, not mentioned. So let's assuming, let's say this one is solid cylinder in that case. So at this particular point, current from the magnetic field from the axis will be taking. So magnetic field from the axis will be taking. So this side, inside point magnetic field is proportional to r. Just now we saw that inside point magnetic field is proportional to r, and outside point magnetic field is inversely proportional to r. So here the variation of the magnetic field in the inside and outside region of the wire. So inside region and outside region of the wire. So inside region uniform, no, it is proportional to r. A linearly increasing function of distance up to the boundary of the wire. Yes, so this is the boundary of the wire. So from this point to this point it will linearly increase, that is B is proportional to r. From this point to this point it will linearly increase, B is proportional to r, and once we come outside the wire it will inversely proportional, then it will decrease and linearly decreasing for the outside region. So answer is option B. Okay, a linear increasing function of distance up to the boundary of the, and then decreasing on with 1 by dependence or outside region, then linearly decreasing for the outside region, a linearly decreasing function. So here it is increasing up to r, and then decreasing 1 with the 1 by r dependence of the outside region. Okay, already I mentioned 1 by r, so we'll be clicking on this because it is directly proportional to like this, then B is inversely proportional to 1 by r. Okay. Next, we have a long straight wire of radius A carries a steady current I. The current is uniformly distributed over its cross section. The ratio of the magnetic field B and B dash at the radial distance A by 2 and 2A respectively. So radial distance A by 2 and 2A respectively. From the radius, at this particular point, if I am going this particular point A by 2, this point is inside or outside, this point will be inside. So what is magnetic field inside formula? The magnetic field inside formula is given by, that is mu naught I divided by 2 pi. So magnetic field inside formula is given by mu naught I divided by 2 pi radius chi square. So what is radius chi square into small a? What is radius chi square into what is distance? This will be A by 2. So this particular, and what is magnetic field outside, that will be getting mu naught I divided by 2 pi. So what we are getting here, 2 pi. What is outside distance? This is 2a. So this will be 2a. So what we are getting, this a and this a cancel, that is mu naught I divided by 2 pi into 2, that is 4 pi a. So this will be 4 pi a, and whatever this one, that is mu naught I divided by again 4 pi a. So luckily what we are getting, outside distance is how much? 2a, and this will be a by 2. So luckily what we are getting here, outside and inside both are having same. So what is the ratio? That will be 1 raised to 1. This one is outside, this one is inside. This one is inside, this one is outside. So we are getting 1 raised to 1. So let's see some more problem from the, so Ampere's law we got. Next we have this Biot-Savart law, some more problems from it. A very long conducting wire is bent in the semicircular shape from A to B as shown in the figure. The magnetic field at point P for steady current configuration is given by. So this current value they have mentioned here is I in this particular direction, and this side again current is I in this direction, and this is the direction of current over here. So how many portion here we have? We have 3 portions. So this one is semi-infinite, and this is also semi-infinite, but this one is curve portion. So first let's talk about 1, 2 and 3. Quickly we can solve it. So because of 1, let's check it. What is direction of magnetic field? So this is direction of current is this way. So direction of current is this way. At this particular point we want to calculate magnetic field. So this is the direction of the current. So this will, okay, I have to rotate my fingers, right? So this will be direction of the current, and I can't rotate like this. I have to go. So this will be, my magnetic field is coming outward like this. So this, for this current, magnetic field is coming outward. For this current, again let's check it. For this current the magnetic field is, wait. So for this current the magnetic field is going into the plane, yes or no? So this is the direction of the current, and magnetic field is going into the plane like this. So for this current magnetic field will going into the plane, okay? And for this current also, magnetic field is going into the plane, both will be added. So let's check this. What is B1? Because of the semi-infinite wire, mu naught I divided by 4 pi r is equals to B3. What is B3? Mu naught I divided by 4 pi r, where r is the distance of this particular point. Because of this semicircular wire, so what is B2? B2 is equals to mu naught I divided by 4 r. What we have to calculate because of all them? We just will be adding this. So B net, what is B net? But what is direction of this? The direction of this is we have to rotate our fingers in this particular direction. This will be coming outward like this. So rotate your fingers in the direction of the current. Current is flowing like this. Thumb is coming outward. So direction of magnetic field because of this second portion of the curve wire we have outward. So this one will be outward. So both this one is inward and this one is also inward. We have to add this. So this mu naught I divided by 4 pi r. Okay, mu naught I divided by 4 pi r plus mu naught I divided by 4 pi r. But we have to subtract this one. This one we have to subtract it. Minus mu naught I divided by 4. Right. So we are getting this mu naught I by 4 pi. Answer should be, if I talk about this mu naught I by 4 per common. So this side pi wala term. So mu naught I divided by 4 r common. So this side 1. So this will be, this particular term we are getting, this particular term will getting 2 by pi minus 1. So this is going into the plane. This is going into the plane. If this one is going into the plane, so this particular term will coming out of the plane. Okay, that one is going, this one is going into the plane, so that will be coming out of the plane. Right. Next we have a current loop consists of two identical semicircular parts, each of radius r, one lying in the xy plane and other lies in xz plane. If the current in the loop is I, the resultant magnetic field because of this. So one line xy plane. So here we have to make this particular things, that is this one is x, y and this will be z. The one line xy plane. So this is one line in xy plane like this. Okay, fine. Second line in xz plane. So second line in xz plane. Second is like this. So because of this magnetic field outward, okay, because of this magnetic field is outward, and because of this magnetic field will be towards this side. So because of this magnetic field will be upward, and because of this magnetic field will be outward. The angle between, so because of this magnetic field, let's say current is this way, okay, current is this way. Because of this magnetic field will be outward, which is coming outward like this. Okay, next, and because of this current carrying wire, the magnetic field will be upward. So this, because of this it will be upward. So one is upward and second is outward like this. So what is angle? So one is upward and second is outward like this. So this is also B and this is also B. Angle is 90 degree. So this will be how much? root 2 times of B. So net magnetic field is how much? Root 2 times of B. Root 2 times of B. What is B? Mu naught I divided by 2R. The answer is option 4. Okay, mu naught I divided by 2R. 2 by root 2, that is root 2 by 2. So this next particular question, again the question is coming from the Biot-Savart law. So this, the current is coming like this, entering this, going like this, and again coming like this. So let's focus on different term over here. This is portion 1 and this is portion 2 and this is portion 3. So because of portion 1 of the wire that we are calculating, direction of current is inward. At this particular point, magnetic field will be downward. Magnetic field will be downward. Next, the current is coming outward like this. The current is coming outward like this. Because of this, again the magnetic field at this particular point will also be downward. So because of 2 it will be downward. Because of this third one and first one is downward. Because of the second one it is going inside. So let's talk about this B1. So what is B1? That is mu naught I divided by, this is semi-infinite, so this will be mu naught I divided by 2 pi r. And what is B3? Again mu naught I divided by 2 pi r, 4 pi r, because semi-infinite is there, not 2 pi r. So this is mu naught I divided by 4 pi r, and this is also mu naught I divided by 4 pi r. If I am adding this to the net magnetic field, will be getting here mu naught I divided by 2 pi r because of this straight portion of the wire. And what is direction is downward side. What is downward side? Negative z. Negative z means minus k cap. Okay, negative z means minus k cap. Next we have, because of this portion, the current is this way. Magnetic field should be going inside. Magnetic field is going inside. So B value is given by mu naught I divided by 2r. Here it will be 4r. Okay, here it will be 4r. And what is the direction of this? The direction of this will be, that is going into this. This will be minus I cap. So that's it. Let's check it which will correct answer over here. So if I take the minus common, this side mu naught I by 4 pi r, pi I cap plus 2 k cap. This one. So this I cap should be negative. So here also 1 and here also 1, you have to check it. And this j cap should be positive. So this total, this also should be negative. Both are negative. Answer is option. Clear? Right. A closely packed coil having 1000 turns has an average radius of 62.8 centimeter. If the current carried by the wire of the coil is 1 ampere, the value of the magnetic field produced at the center of the coil. What is magnetic field at the center of the coil? Here we have solenoid. We have to use the formula of the solenoid. What is formula of the solenoid? We have B is equals to mu naught N I. So that's it. What is mu naught value? 4 pi into 10 to the power minus 7 into, what is, how many tons it has? 1000 tons. Has an average radius of 62.8 centimeter. 1000 tons. They have not given the length of here. So they have given the radius of this. What is radius of this? 62.8. So let's talk about this. What is N? Number of tons per unit length. So this is closely packed and has an average radius of 62.8 centimeter. If the carried by one value, so we have to find the length over here. So what is the length? How can we calculate the length? They have given the radius 62.8 centimeter. Whose radius? This particular radius. So has an average radius of 62.8 centimeter, right? So we can solve this particular question like N is capital N divided by length. N is the number of tons per unit length. So there they mention closely packed coil having 1000 tons has an average radius of 60. Okay, so this is not the question of the solenoid. Just a second. This particular questions that we'll be solving using this coil also. They are given the closely packed coil 1 ton, 2 ton, 3 ton, 4 ton. Like that, how many tons they have mentioned? 1000 tons they have mentioned. The radius they have mentioned, this radius is 62.8 centimeter. So next, if you talk about this, they are asking what is value of the magnetic field at the center. So magnetic field at the center is given by, because of this particular coil, that is P naught N I divided by 2 into R. So this I will be writing this 4 by into 10 to the power minus 7 into number of tons is how much? 1000 into number of tons is 1000 into I is 1 ampere divided by radius 2 into radius. What is radius? 62.8. 62.8 into 10 to the power minus 4. So here this one is pi 3.14 and this is 62.8. This is 1 ja and this will be 20 ja. Okay, this will be 20 ja. This one is 2 and this will be 4 cancel. We are having 10 remaining here. So this we are getting approximately 10 to the power minus 7, 10 to the power 3, that is 10 to the power minus 4 divided by 10 to the power minus 3. So we are getting this 10 to the power minus 1 Tesla. Answer is 10 to the power minus 1 Tesla. Because of this magnetic field we are calculating 10 to the power minus 1 Tesla. The magnetic field on the axis of the circular loop of radius 100 centimeter. So on the axis of the circular loop of the radius 100 centimeter, they have mentioned the radius of the this particular wire is how much? 100 centimeter, carrying a current of root 2 ampere at point 1 meter away from the center of the loop. So this particular point, how much distance? 1 meter away. This particular point they're asking center of the loop. They're asking what is the magnetic field? What is magnetic field at this particular point? So magnetic field is given by mu naught I into R square. Actually, in general formula is this mu naught Ni into R square divided by 2 into R square plus X square to the power 3 by 2. This particular formula will be using when the magnetic field they're asking at a distance, how much distance? This particular at a distance of 1 meter from the center that we have to take, and radius should also be given. So radius is also how much? 1 meter. Putting the values, the magnetic field is given by mu naught into Ni. So mu naught into number of turns they not mentioned, take it as 1. Current value is root 2 into radius. What is radius value? That is 1 square divided by 2 times of this 1 square plus 1 square to the power 3 by 2. So magnetic field that we are getting in terms of this mu naught, you write in terms of this 4 pi into 10 ki power minus 7 into this side root 2 divided by 2 into R square plus X square, that is 1 plus 1, 2 to the power 3 by 2, 2 root 2. Okay, 2 root 2. So this side 2 root 2. So this root 2 get cancelled over here. We are getting this also getting cancelled. So magnetic field B is equals to pi into 10 ki power minus 7, pi into 10 ki power minus 7. What is pi value? 3.14 into 10 ki power minus 7. Okay, this is the magnetic field because of this circular current coil on axial line. So next question is here: a tightly wound 1000 tons of radius carries a current of 7 ampere. A tightly wound 1000 tons of coil of radius 10 centimeter carries a current of 7 ampere. The magnetic field of at the center of the coil should be given by. Okay, again this particular question we can solve. Again the same question is there. So this is how many tons? How many tons is there? This is 100 tons is there. And what is the radius? The radius value they have mentioned is 10 centimeter, that is 0.1 meter, that will be calculating. Now carries a current of 7 ampere. Carries a current of 7 ampere. The magnetic field is the center of the coil. They're asking what is at the center of the coil magnetic field. How can we calculate this? Again, mu naught I divided by 2R multiplied by N. N is the number of turns. Putting the values directly. So 4 pi into 10 ki power minus 7 into I value. How much I value? 7 into. Putting this. Okay, let's calculate this. So be smart in putting the values of the pi because they have given 7 also. I can write here 4 pi into 10 ki power minus 7 into. So this particular term multiply by number of turns. What is number of turns? Multiply by 7. Okay, what is number of turns? How many turns? We have 100 turns divided by 2 into R. What is R? R is 10 centimeter, that is 0.1. That's it. So solving this particular case, pi value we can write here 22 by 7. So this 4 into 22 by 7 into 10 ki power minus 7 into 100 divided by 0.2. 7 cancel, we are getting this. So this one is 88 and this is, so this will be something like we are getting in terms of the 440. If we cut this into 10 ki power minus 5 we are getting. So we are getting the range of 440 into 10 ki power minus 5. So okay, 440 into 10 ki power minus 5. So this I can write here 4.4 into 10 ki power minus 3 into 10 ki power minus 3. Yes or no? So this we can write it in this case. So this is 4.4 Tesla, millitesla, right? So answer is option C, 4.4 millitesla, right? So next topic, that is the force on the moving charge in magnetic field. We discussed the Biot-Savart law, we discussed the Ampere-Sartre law, and we discussed some of the questions on that. Let's discuss the force on the moving charge. If magnetic field exists and the charge's particle is moving with velocity v and angle is theta over here, the force is given by q times of v cross b. Force is given by q times of v cross b if velocity is parallel to magnetic field. So we will discuss the different cases over here. The case one, what is case one? The case one that we will be discussing, if velocity is 0 means charge particle kya hai? The charge particle at rest. Charge particle at rest means it is not at all moving. In that particular case, whatever the magnetic field we are giving, the charge particle is not at all moving. The magnetic force value will be 0 because F is 0 because velocity is 0. This is in vector form, and what is in scalar form that we are writing here? QVB sin theta. Force is given by QVB sin theta, and this force is 0 when the charge particle is at rest. Different case number 2, if velocity is parallel to magnetic field. In that case, if the charge particle velocity is parallel to magnetic field, it is moving in the same direction of magnetic field. then what is the force? Again, it will be 0, because angle theta is the angle between, whose angle? Angle between velocity and magnetic field. Theta is the angle between velocity and magnetic field is 0, because both are moving in the same direction. The magnetic field exists in the direction of the velocity, so here theta equals to 0, that's why force will be 0. This is the second case. Third case, suppose if we have theta is 90 degree. When the theta is 90 degree, charge particle will be moving in a magnetic field in such a way that it will complete a circular motion. The charge particle will be moving in a magnetic field, it complete a circular motion like this. And when it is completing a circular motion, this charge particle is moving in a circular path. So when it is moving in a circular path, the centripetal force is given by tangential force, that is force is given by QVB. From that we will getting force F equals to QVB, and from here we are getting this mv squared by r. So from here we got r equals to, what is that? mv by qb. The radius r equals to mv by qb, where m is the mass, v is the velocity, q is the charge, and b is the magnetic field. So radius formula in this case mv by qb. We can also write here p by qb. The first term, that is p is equals to mv, and what is that? Under root. So second, so p is equals to mv, we can directly write from here. Just a second. So this one, p is equals to m in multiplied by velocity. Second is p is equals to under root 2mk, where k is the kinetic energy, q is the kinetic energy. Third particular point that we'll be writing here, p is equals to, so what is p is equals to? Under root 2m q into v. Why q into v? Because kinetic energy is given by kinetic energy is charge multiplied by potential difference. So from here the radius is given by under root 2m q into v divided by 2 under root q into v divided by q into v. So depending on the different questions, we'll be applying the different formulas over here. Whenever charge particle is moving, when the theta is 90 degree, when the charge particle enters the perpendicular to magnetic field, the speed will be constant. So it is doing uniform circular motion. When it is doing uniform circular motion, what are the terms? That is kinetic energy, speed, its momentum will change, velocity will change, acceleration will change, speed will remain constant. Speed remain constant, speed comes with kinetic energy, the kinetic energy remains also constant. Uniform circular motion हो रहा है यहाँ पे. So in uniform circular motion, when it is doing uniform circular motion, the speed will be constant, and if it is speed is constant, the velocity changes because of the direction, acceleration changes because of direction, but speed will remain constant. That we have to focus, and this properties that we can use. The time period is given by, what is time period in this particular case? The time period, that is time to complete one rotation. So t is equals to 2 pi r divided by v. So t is equals to 2 pi divided by v into what is r? mv by qb. So time period is given by 2 pi m divided by qb. You can check it, that time period does not depend on radius, does not depend on velocity. So here frequency we'll be writing in terms of the time period, that is qb divided by 2 pi m, the frequency of this. Third particular case, when the charge particle is moving at some angle velocity with the magnetic field. So charge particle is moving some velocity with the magnetic field some angle theta. In that case, the charge particle will do what kind of motion? This will be doing helical motion, helical path. This will be doing helical path. And what is the radius of that particular path? It will be having two components. One component is along this direction, that is v cos theta, and one component is along this direction, that is v sin theta. This v sin theta is trying to rotate it, and v cos theta is taking it forward direction. So I will be writing this radius of this particular path mv sin theta, okay, divided by qb. mv sin theta divided by qb, where q is the charge, b is the magnetic field. And what about the pitch? We define the pitch, the distance travel in one rotation. The distance travel in one rotation, that is pitch, that we define x is equals to v cos theta multiplied by time period. So this x equals to v cos theta multiplied by time period. What is time period? 2 pi m divided by qb. The distance traveled by the charge particle in one rotation is what we define pitch. So these are the formulas that we have when the forces are there in magnetic field. So let's see Lorentz force. What is Lorentz force? When both electric field is present and magnetic field is also present. So both electric field and magnetic field is present, magnetic field also present. In that case, if the charge particle is also exists and having some velocity, then we define Lorentz force, that is the combination of the magnetic force and electric force. So this is what we define Lorentz force, and that is given by electric force, magnetic force q into v cross b plus electric force q into e. This is the Lorentz force, combination of electric field and electric force and magnetic force. Now suppose if we write this, if electric field is also there, case 1, what is case 1? We have to take different cases, velocity, magnetic field and electric field. Three different variables we have, they are either parallel to each other or not parallel to each other. We have to take different cases. So in that case, first one, that is velocity is parallel to magnetic field, the magnetic field is parallel to velocity, and electric field is parallel to magnetic field. All three are parallel to each other. In this case, I will be writing what will happen. The magnetic field is there, electric field is also there, and charge particle also moving in the same line. So in this case, what will happen? No force will be acting because of the magnetic force. In this case, magnetic force will be 0. Okay, no deviation of the charge particle. Electric force will be there. Electric force will always be there. That is Q into E. So charge particle will move in a straight line with varying speed. The speed might vary depending on the direction of the acceleration. So next we have that this is the case 1. What is case 2? Case 2 I am discussing when if all are perpendicular. If E is perpendicular to B, the B is perpendicular to E, and V is perpendicular to V is also perpendicular to E. When all are perpendicular to this case, and velocity is given by E by B. So when this condition is satisfied, charge particle will move in a straight line. Charge particle will move in a straight line without any deviation. Will move in a straight line with constant speed. Okay, with constant speed. Will move in a straight line with constant speed. So let's see some of the questions from this. That is, a particle of mass m charged with kinetic energy T enters a transverse uniform magnetic field of induction B. After 3 seconds, the kinetic energy particle will be. After 3 seconds, the kinetic energy particle will be. I told you it is doing uniform circular motion when transverse means what? Perpendicular magnetic field. Theta is 90 degree wala case. So when the theta is 90 degree, it is doing uniform circular motion. What is initial kinetic energy? T. So what should be final kinetic energy? It has to be T because kinetic energy is constant. Remember this. The particle is doing uniform circular motion. In uniform circular motion, the speed does not change, velocity changes because of its direction. Uniform circular motion, the speed does not change but velocity changes, so this has to be T. Ionized hydrogen atoms and alpha particle with the same momenta enters perpendicular to constant magnetic field. The ratio of the radii of their path. What is the radius? The radius will depend on mv by qb, and one more formula that we discussed, that is mv under root 2m kinetic energy. One more formula divided by this. Particle with the same momenta perpendicular to magnetic field. Same momenta. Okay, momenta is same. So not required. This one is not required. They are having same momenta. So radius is given by p by qb. So in this case, when the radius is p divided by qb, we can check radius is inversely proportional to charge. Magnetic field is same. They are having same momenta. That is, first one is ionized hydrogen and second is alpha particle. Both are having same momenta. Both are having same momenta. Radius of the hydrogen should be equal to radius of the alpha particle. So not radius. What? Same momentum. That is, momentum of the hydrogen should be equal to momentum of the alpha particle. Okay. So this they have mentioned in this particular case. So radius is inversely proportional to charge. So how can we calculate this? So radius R2. So radius R2 by R1 is equal to Q1 by Q2. So we are finding the ratio of what? RH by R alpha. So RH by R alpha. RH by R alpha. RH by R alpha is equal to Q alpha by QH. That's it. What is Q alpha? We have charge of alpha particle. All of you know this. Alpha particle charge is 2e and hydrogen charge is E. So this is 2 raised to 1. Okay, answer is option D, 2 raised to 1. So all of you know this. I hope this alpha particle charge will be 2e, mass will be 4 times mass of proton. If we talk about the proton, proton will be having charge E, mass is mp only. If we talk about the neutron, neutron does not have charge, mass is, we can write here mp. If we talk about the electron, electron is having charge E only, minus E, and this is mass of the electron. And we know the values also. Mass of the electron is 9.10 to the power minus 31. Proton is 1.69 to the power minus 24. A proton and alpha particle both enter region of uniform magnetic field B, moving at right angles to the field. Yes, they are moving in a circular path. Okay, right? Both are moving circular path. The radius of the circular path of both the particle is equal. So both are having same radius. That is, radius of the proton should be equal to radius of the alpha particle. So one is alpha particle and second is proton. And kinetic energy acquired by proton is 1 mega electronic volt. The energy acquired by the alpha particle should be given by. They are asking the energy, they have given the radius. So how can you find this? We know this particular relation. What is the relation? R equals to under root 2m kinetic energy divided by Q into B. Squaring both the sides. So this will be getting R square equals to 2m kinetic energy divided by Q square B. Kinetic energy expression that we are getting here. Q square B square R square divided by 2m. R square divided by 2m. Q square B square R square divided by 2m. So Q square B square R square divided by 2m. So kinetic energy is depends on these quantities. So let's focus on what we have. So next is, they are having same radius, they are having same magnetic field, mass will be different. So kinetic energy is proportional to square of the charge divided by mass. And if I talk about the alpha particle is having 2e chi square divided by 4mp. Okay. If I talk about this proton, alpha particle will be 2e square divided by mp divided by this side kinetic energy of the proton. Again, this will be e square 4mp. This is e square divided by mp. So this will get cancelled everywhere. We are getting cancelled. So answer is 1:1. So if proton is having energy of 1 mega electronic volt, then alpha particles are also having energy of 1 mega electronic volt. Clear? Next we have this one. A uniform electric field and uniform magnetic field are acting along the same direction in a certain region. If an electron is projected in a region such that its velocity is along the direction of the field, then electron, again this is the case number 1, electric field is there and magnetic field is also there. Electric field is there, magnetic field is also there, and electron is also projected along the same direction. Now, because of the magnetic field, as the velocity of the electron and magnetic field are parallel, no magnetic force will be acting on the electron, only the electric forces will be acting, and that will be opposite to direction of electric field. So if electric field is exists this way, the magnetic force will be acting this, electric force will be acting this way. That is, force F equals to E multiplied by capital. Okay, so this is E multiplied by capital E. This is the force that will be acting over here. Now, so what will happen? Will turn towards the right of the direction of motion, will turn towards the left of the direction of motion. Speed will decrease because force is acting on the back side. It is traveling towards forward direction. Force is acting on the back side. Speed will keep on decreasing. Okay, speed will keep on decreasing. So next question, let's solve. A particle of mass this much and charge this much. The particle is given initial velocity this much. In the presence of electric field and magnetic field, to keep the particle moving in the horizontal direction, it is necessary that the first condition is that electric field should be perpendicular to magnetic field, the magnetic field should be perpendicular to velocity, and the velocity should be perpendicular to electric field. So this, both E and E are mutually perpendicular and perpendicular direction of velocity, and after this also one condition is there, V is equals to E by B. So when this condition is satisfied, what will happen? The charged particle will continue to move in a straight line. So option 3 is the statement is correct. Let's talk about this. B should be perpendicular to direction of velocity and E should be along the direction of velocity. B should be perpendicular to direction of velocity and E should be along the direction of the velocity. No. So if B is perpendicular to direction of velocity, so if charged particle is moving this way and velocity is this way, magnetic field is perpendicular. So what will happen? It will move in a circular path because of this 90 degrees. So this answer will be wrong, because if both are perpendicular, it will move in a circular path. Both B and E are should be along the direction of velocity. Yes, just now I told, if it is in the same direction, only the electric force will be acting and electron will be moving with constant velocity. So this 2 is also correct. B should be along the direction of velocity, E should be perpendicular direction of velocity. Even if E is perpendicular direction of velocity, if this is the velocity direction and E is this direction over here, this angle is 90 degree, this will deviate like this. This will be in parabola, not moving a straight line. This option also wrong. That option C, both 2 and 3 is correct one. So force on current carrying wire, if the wire is carrying current like this, and if wire is carrying current like this, and magnetic field also exists in this particular region, and B, and let's say this particular angle is theta. So here we define force on the wire is given by I into L cross B. What is L here? L is the length vector in the direction of the current, and B is the force is given by ILB sine theta. ILB sine theta. If theta is 90 degree, in that case we'll be writing force is equals to I into L into B. What is theta here? Again, theta is the angle between the magnetic field and length vector. This is the length vector in the direction of current and this magnetic field. Now ILB sine theta, theta is the angle between I and B, we can see current and magnetic field के बीच का angle, that is theta. Next we have, that is A mass of 250 gram is suspended horizontally in uniform horizontal magnetic field of 0.7 Tesla. So there is one straight wire, the length of the wire is L, and the amount of current flowing through wire will be given by, it is suspended. So downward force will be acting, that is mg. And it is, let's say current is flowing like this. And it is suspended in which magnetic field? Horizontal magnetic field. Uniform, horizontally in uniform magnetic field. And magnetic field is inside, let's say. So in this case, magnetic field is inside. So because on this particular case, again direction we have to consider like this. This direction of the current. This is the magnetic field which is going inside. Upward will be upward. So in this case, the upward direction we have to take it as F. What is F? BIL. And downward force is mg. So both the forces has to be equal because it is stationary. BIL, that is current is flowing here I, and magnetic field is B. So BIL equals to mg. So what is I value? I value is mg divided by B into L. So what is mass? The mass value, everything that we know here, that is mass is 250, 0.25 into G value is 10 divided by B value 0.7 Tesla multiplied by L. What is L here? Length is 2. So solving this particular question will be getting approximately, what is the answer we will be getting? So we are getting this 2.5. So 2.5 divided by 0.7, 1.4, that is 25 by 14. So answer will be 1.75, something like that we will be getting, 1.75. 0.7 Tesla into 10, we are getting 9.8. If we are taken, we would have got the answer. Right, anyway. So this anyway answer will be 1 point something, that is 1.75. An arrangement of 3 parallel straight wires placed perpendicular to the plane of the paper carrying the same current I along the same direction as shown in the figure. Minor the force per unit length on the wire. So here we define if 2 wires are there, so one wire like this, one wire also like the distance between them is d. Then here we define force per unit length, not exactly force, force per unit length. If both the wires are carrying the current in the same direction, both will attract each other. Both the wires are carrying current in different direction, both will repel each other. So here the force of attraction in this case will be given by force per unit length is given by, that is mu naught I1 into I2 divided by 2 pi d. I1 into I2 divided by 2 pi d. So this will be writing this mu naught I2 divided by 2 pi d. So here we have how many wires? Here we have 3 wires. One wire like this way, one wire this way, and one wire this way. Both are carrying current in outward direction. You can check this current, and this current. Both are carrying current in outward direction. So because of these wires, we want to calculate magnetic field. So this wire will attract this wire towards this direction. So let's say this force is force per unit length. I am writing here Fc by L. Okay. And what about this wire? Again, this wire will also attract this wire in this particular direction. This will be force Fb by L. So what they are asking? Net force per unit length. So this side, again, this particular force, distance is d, so this will be same and this will also be same. So this will be root 2 times of F by L. And what is the value of this? Mu naught I1 I2 divided by 2 pi d multiplied by root 2. Why root 2? Between these two forces, that is mu naught I1 I2 divided by 2 pi d. Between these two, mu naught I1 I2 divided by 2 pi d. Multiply how many times? Root 2 times of this. So this will be root 2 times of this. Answer will be I1 I2 is also same. So this root 2 by 2. So this mu naught I square divided by root 2. This will be correct answer over here. Clear? So this is the net force that is acting on because of this toward this side. This will attract toward this side. This will also attract toward this side. As the angle is 90 degrees, this will be root 2 times of this. Clear? So this question, that is a square loop ABCD carrying a current I is placed near and coplanar with a long straight wire. So this one is the long straight wire. It is going towards the sky and towards this side, downward side. So this is a long straight wire. Because of this, what we have to find? Net force on the loop will be given by. So first thing is that very clear. Because of this, magnetic field exists in this way. The magnetic field exists in this way. Like this, there will be magnetic field. Okay. If I talk about this particular point, the magnetic field value is same. This particular point, the magnetic field value is same. This point, magnetic field value is same, and corresponding at the same distance on the downward side, all the points on this have pairs on this over here. So magnetic force acting on this upper portion is, let's say, in which direction? The magnetic force is acting on the upper portion. In this case, that will be upward. And this magnetic force that is acting on this magnetic field is going inward. So this is the direction of magnetic field. And this direction of the current, magnetic field is going inward into the plane. and this direction of the current, this side it will be, this will be force, this will be force. This force and this force will cancel each other. Okay, this force and this force will cancel each other because equal in magnitude and opposite in direction. So this force and this force will cancel the remaining, this two, remaining this force, this one and this one will attract each other like this, and this one and this one will repel each other like this. That's what we have to calculate. What is the length of this? We can write. So here, if we talk about the force on AB by length L is equals to mu naught I into small I divided by, what is distance here? 2 pi into L by 2. So this side mu naught I into small I divided by 2 pi into L by 2. This is, what is direction of this? This is towards left. Okay, this will be towards left. Second one that will be calculating here. So this wire distance from here will be given by, so that will be writing, this is F, I will be writing this F CD by L. So this will be calculating here mu naught I into small I divided by 2 pi, what is distance from here? L by 2 plus L, that is 3L by 2, will be writing this. So this will be 3L by 2, and this is towards right side. What we have to write? So this L will go multiply net force, the net force will be writing this minus this. So mu naught I into small I into L divided by 2 pi L by 2 minus mu naught I into small I into this side, small I into L divided by 2 pi into 3L by 2. So this particular value, this L will get cancelled. So we are getting this mu naught I divided by pi, or pi 2 pi cancel, this will be pi, minus mu naught I into small I divided by 3 pi. So this we are getting here, answer will be 2 by 3 mu naught I into small I divided by 3 pi. So next we have magnetic moment. What is magnetic moment? We define the magnetic moment is defined as I multiplied by area. The current multiplied by area is what we define magnetic field. And if we have number of turns is also there, M equals to N multiplied by I multiplied by A. So this is the magnetic moment, N multiplied number of turns into I, current, area, A is the area of the loop. The uniform conducting wire of length 12A. So here we have wire. So let's talk about this one first. So here we have wire. What we are doing? Resistance R is wound up as current carrying coil in the shape of equilateral triangle of side A. Okay, equilateral triangle of side A. So in this case, current is I. Okay, equilateral triangle of side A. So what is it asking? Magnetic dipole in the. So first, what we are doing? First, we are molding in the equilateral triangle of side A. So one, what is total length? The total length is 12A. We are molding in this particular manner. So 12A. So this is side length is A. So A, 3A. So how many turns we can make if we are molding into triangle? So this is 12A. So this total parameter of this triangle is 3A. How many times? Like that 1, 2, 3, 1, 2, 3. Like that we can make mold 4 times. So here number of turns is N. Number of turns is N is 4. The number of times N is 4. How many times we are molding it? 4 times. So what is area of this? Area is given by root 3 A square by 4. This one is area. What is magnetic moment in this case? I will be writing this current multiplied by area NIA. What is N? Number of turns is 4 into I into root 3 A square by 4. Okay. So this 4 and 4 get cancelled. Next, we are molding in form of the square. So when we are molding A. 4A we completed. Like that, how many? 3 turns. So this will be 3 turns that will be having. Okay. So in that case, what is magnetic moment? NIA. So what is N? 3 into what is I? Current I multiply what is area? A square. So from this we are getting root 3 I A square, right? Root 3 I A square. From this we are getting 3 I A square. Answer is option, that is root 3 I A square and 3 A square. A closely wound solenoid up to 2000 tons, that is N equals to 2000 tons, and area of the cross section 1.5 in 10 to the power minus 4. The area of the cross section they mentioned, that is 1.5 into 10 to the power minus 4, carries a current of 2 ampere. So what is total current? I, we are having 2 ampere, is suspended through its center and perpendicular to its length, allowing turn in a horizontal plane in uniform magnetic field. The magnetic field value is given, B is equals to how much? 5 into 10 to the power minus 2. Remember this. So if you have the solenoid, the magnetic field exists. That magnetic field is making how much? So this is the axis, and magnetic field exists in this particular manner, And what is this particular angle? That this magnetic field and this solenoid angle. So this particular angle is how much? 30 degree. So this angle is 30 degree. So theta equals to 30 degree, right? Okay, theta is 30 degree. Next what we have, allowing it turn in magnetic field of this one, be 10 find 10 power minus 2 Tesla, making angle of 30 degree with the axis of the solenoid. The torque on the solenoid will be given by, first thing is that what is torque? The torque is given by, tau is given by m cross b. Okay, what is m? Magnetic moment. And what is magnetic moment ka direction? Direction of this current. If the solenoid is like this, so magnetic moment ka direction will be given by direction of this along this particular direction. So rotate your fingers in the direction of the current. So coil will be going like this. Rotate your fingers in the direction of the current. Okay, rotate your fingers. The coil is going like this, current is going like this. Rotate your fingers in the direction of the current. This will give direction of the magnetic moment. So magnetic moment is also along the same direction, that is along the axis. And this angle is theta. So this is the magnetic moment this way, m vector, and this is the b vector, and this angle is theta. So m b sine theta. I will be writing this m b sine theta. And what is m? Magnetic moment. What is magnetic moment? N into I into A. N into I into A. What is N? Number of turns. I is the current and A is the area into B sine theta. So this is the torque that we are having. N I A B sine theta. So what is torque? Number of turns. So what is number of turns we have? 2000 multiplied by what is current? Current value is, just put the values, 2 into what is area? 1.5 into 10 ki power minus 4 into B value again 5 into 10 ki power minus 2 into sine theta, sine 30. So solving this case, we'll be getting the answer of, let's check it. So this 1.5 into 5 into sine 30. So this is 1 by 2. This one is 1 by 2. So this 2 and this 2 getting cancelled. 2000 into 5 will getting 10,000. 10 to the power 4 minus 2 minus 4. This will get cancelled. 10 to the power minus 2. So we are getting 1.5 into 10 ki power minus 2 Newton meter. That is the torque that we are getting over here. Okay, that will be torque we are getting. So this is the value. What is formula? Torque tau is m cross b, and scalar form torque tau is equal to mb sine theta. Theta is the angle between the m vector and b vector. So next we have, that is bar magnetins properties. So what is bar magnet? If we talk about the bar magnet, so we'll be having this magnet over here where the poles will be inside this point M, and this point also M. This is the pole strength, and distance between these two is what we define magnetic moment. So this we call it as pole strength, and this one, this will be pole strength, this also pole strength. Then here we define magnetic moment. What is magnetic moment? Pole strength multiplied by magnetic length. And what is direction of this? Direction of this we will be having, one is south pole and second is north pole. So if this one is south pole and this one is north pole, the direction is always from south pole to north pole. Remember this. So on cutting this bar, this will be south pole and this will be north pole. The magnetic monopole does not exist. The bar magnetic moment does not exist. This is the Gauss law for the magnetism. So if I cut this particular magnet, what will happen? If I am cutting the magnet, again we will be getting two poles, south pole, north pole. Again this side also we are getting this north pole and this will be south pole. So sorry, this will be south pole and this will be north pole. Again if you are cutting like this, so again how we are cutting this? When we are cutting like this, what will happen? If you are cutting like this particular along its axis, so this length will be reduced by L by 2 and this length will also be reduced by L by 2. Pole strength remains same, magnetic moment and this pole strength remains same, but magnetic moment will be given by M into L by 2, so that is capital M by 2. In this case also, pole strength remains same, M into L by 2, but magnetic moment will change, that is capital M by 2. Suppose on the other side, if I cut like this way, so just now we have cut it this way. Suppose on the other hand, if we cut this way, if we cut this particular way, so that small pieces, so this particular magnet, I have magnetic pole strength M, this also pole strength M, the length is L. In that case, what will be writing? What is magnetic moment? So pole strength is initially is M and this also M. If we are cutting along this, we are decreasing the cross section area of the bar magnet. So when we are decreasing this cross section area of the magnet, this particular will reduce by M by 2. So this will also be M by 2 and this will also be M by 2. And distance is how much? L. Distance remains same. So what is new magnetic moment in this case? M by 2 multiplied by L. So what is this? I will be writing here capital M by 2. What is magnetic moment initially? M into L. So in this case, again it depends on how we are cutting this. So magnetic moment of a bar magnet is M, it is now bent in a such way that it forms an arc section of circle subtending an angle of how much 60 degree at the center. Okay, fine. So initially we have the magnetic moment like this. Initially we have a magnetic moment of an iron bar. We have the magnet like this, suppose. Okay, if you have the magnet like this will be south pole and this will be north pole. They will be having some distance between them. What is the distance between them is, let's say length is L. Okay, so what is magnetic moment? Here I can write here M multiplied by L. Now what we are doing, we are bending in such a way that it forms an arc of section. And what is that arc? How much angle it is subtending in the center? That angle is 60 degree. Okay, this angle is 60 degree. So this particular point north pole and this will be south pole. This distance that we have to find over here. And if this angle is 60, this one is radius, this one is also radius, so this will also be. So always remember, now we'll be writing the magnetic moment will be M multiplied by distance between these two. What is distance between these two? That is R. Now you'll be asking, sir, what is this R? How can you get the R? So how can you get the R? So this length will not change, right? So this length will be L. So here we can write here L equals to R multiplied by theta, where theta should be in radian. So L equals to R, theta in radian means this will be pi by 3. Has to be in radian. So from here R we can write 3L by pi. So M dash is equals to M into R. What is R? 3L by pi. So this will be 3 capital M divided by pi. What is M here? Original M is. So this is M dash 3 capital M divided by pi. Answer is option A. So next is bar magnet in uniform magnetic field. So if bar magnet is placed in uniform magnetic field like this, okay. So when the bar magnet is placed in uniform magnetic like this, and let's say this is south pole and this will be north pole of the magnet. So this angle is theta. So magnetic moment is south pole to north pole, and magnetic field is this way. So here we define certain terms. What is that? First term, torque. So what is torque? The torque is defined as vector form, that is P cross E. No, not P, M cross B. M is the magnetic moment, M cross B. And if I write the magnitude of this, the torque is given by MB sine theta. Okay, this is torque. If we talk about the potential energy of this, that will be given here. The potential energy of this is given by M minus of M dot B. So that will be writing here minus MB cos theta. Minus MB cos theta, that will be potential energy of given magnet in uniform magnetic field. If they are asking work done in rotating from theta 1 to theta 2, in rotating from theta 1 to theta 2. So this particular formula, that is MB cos theta 1 minus cos theta. So let's check what the question they are asking in this particular way. So this will be writing that it's an equilibrium state. Let's check what is equilibrium. So if this is the magnetic field that exists in this particular manner, okay, and if the bar magnet lies along this side, so this will be south pole and this will be north pole. If the magnetic moment and this, what is theta? 0. The magnetic moment and magnetic field both are having the same direction, theta value is 0. What is torque? MB sine 0, it will be 0. What is potential energy? Minus MB cos 0. So this potential energy is equals to minus M into B. This particular orientation we call it as stable equilibrium. This will be stable equilibrium. So if we have next one like this one, the magnetic field in the same direction, but we are just reversing the direction of the magnet. So magnetic in the such way that south pole is this way, north pole is this way. Direction of magnetic moment this way, magnetic moment this way, M vector this way, and this will be, this is magnetic field vector. So right now the angle between the magnetic field vector and this is 180 degree. So and when it is 180 degree, this is what we define torque. What is torque? MB sine 180, and this particular term will be 0 anyway. What is potential energy? Minus MB cos 180, because angle is 180 degree. In that case potential energy will be clear. In that case potential energy will be 0. So from here the potential energy will be 0, not 0. Potential energy equals to, potential energy is equals to, how much we are getting this? This is minus 1, this is also minus 1. This will be MB. So here the potential energy is maximum. This particular orientation we call it as unstable equilibrium. This will become under unstable equilibrium, right? So let's see what this question is saying. So this one, sorry, not this one, right? A bar magnet is hung by thin cotton thread in uniform horizontal magnetic field and it's in equilibrium state, Right now it is equilibrium state, means magnetic moment and magnetic field both are in the same direction. It is like this way, south pole and north pole both are in the same direction. The energy required to rotate by 60 degrees is W. So how much energy is required to rotate? So right now what is the energy required to rotate? That is W. We'll be writing this MB cos theta 1 minus cos theta 2. Putting this value, how much we have to rotate? We have to rotate by how much angle? 60 degree. Okay. So M into B cos 0 minus cos 60. So this W is equals to M into B cos 0 1 minus 1 by 2. How much you got? So W is equals to MB by 2. Okay, W equals to MB by 2. Second case, W equals to MB by 2. Now the torque required to keep the magnet in this position. So what is the torque in this particular position? Torque is MB sine, what is theta? 60, right? It has to rotate by how much angle? 60. So what is theta? 60 degree. So this is root 3 MB by 2. What is MB by 2 value? W. So what is torque? Root 3 into W. I hope this is clear. So this one is root 3 into W. So next we have some of the properties that we have for the diamagnetic, paramagnetic, and this last part of we have diamagnetic, paramagnetic, ferromagnetic. I am suggesting you go through this. What are the different terms we have? Diamagnetic are the substances which have that are feebly repelled by the magnetic field. They are feebly repelled by the magnetic field. What is paramagnetic? They are weakly attracted by the magnetic field. And what is ferromagnetic? They are strongly attracted to the magnetic field. Magnetic moment of the atoms, mostly for diamagnetic material it will be 0, and for paramagnetic material it will be non-zero, and for this ferromagnetic material it will be large and non-zero if it is ferromagnetic material, because here in the electrons are paired and here electrons are unpaired. Some electrons are unpaired, so here net magnetic will be with 0. The behavior we have weak and negative, yes, and this is weak and positive, and this is very strongly positive behavior in case of magnetic field. So these are the points we have. Let's discuss this one. There is susceptibility. When we discuss the susceptibility, zeta value is negative for diamagnetic substance, small and positive for paramagnetic substance, and large and positive for ferromagnetic substance. Zeta value, that is magnetic susceptibility. So these are the examples we have, and examples we have bismuth, copper, lead, water, and these examples we have for. So just go through this table. I am suggesting you in your module from NCERT, from wherever you are getting this things, that properties of the ferro, di and para, you just go through and revise it. Let's discuss this temperature effect. So in general, zeta value, if I plot the graph of this diamagnetic value, zeta value depends independent on temperature, does not happen on this. No change on the effect of the temperature for the zeta value or diamagnetic substance. If it is paramagnetic substance, zeta value depends like this, that is magnetic property decreases on increase in temperature. Okay, increase in temperature. This zeta is inversely proportional to temperature. Next, this is ferromagnetic substance. The graph will be like this. This zeta versus temperature. So what actually happens on increasing the temperature? It loses its magnetic property. The ferromagnetic property loses at one particular temperature. What will happen? It will become the paramagnetic. So after this side, it will behave as a paramagnetic. Before this side, before this particular point, it will behave the ferromagnetic. So this is ferromagnetic up to this particular point. This particular temperature is also defined Curie temperature. So above the Curie temperature it will become paramagnetic. Below the Curie temperature it will behave as ferromagnetic only. The magnetic property loses with increase in temperature. So that you should remember this. Above the Curie temperature para, below the Curie temperature ferro. So these are the topics that we have discussed today, and I am suggesting you please go through this chapter. Is having together this chapter 3 to 4 questions we can expect from this. And tomorrow we'll be coming with this chapter, that is electromagnetic induction, how the electricity is generated and alternating current. We'll be discussing this Faraday's law, self-induction, and AC circuit, LCR series circuit, different types of circuit is there. This is also a very important topic for this NEET purpose. Right. So that's it for today. Tomorrow we'll be coming with this chapter. So till now, practice well and do your best. That's what I will say from this side.